Hello and welcome to lesson number 12 in Unit 2B, Quadratic Functions, Forms, and Transformations in our grade 11 University College Math class. This is Applications of Quadratic Functions. So this is the point where we take everything we've learned about going back and forth between the three forms of the quadratic and see how they line up with common requests for information from word problems. Because parabolas, as I would talk about in class with you guys, they're all around us. Quadratics, by their nature, having an optimal value, a highest or lowest value, they have applications all across a variety of industries. Some of the more common ones that you might be able to imagine are listed here, like the flare of, or the path of a flare being fired into the sky. So any projectile being tossed will follow the arc of a parabola. Anything that's going to be swinging like a pendulum will model that. The sort of the slant that you see in a satellite dish or a ramp on a roadway, if you're trying to find an optimal value for speed or how to get from one point to another, all of these optimization problems, they are all modeled by quadratic functions, which is kind of amazing. So normally in class we would do this fun little example where I have a student get up on the chair and then the student would jump and we would sort of try to model the path of this student's toe. Since we don't have a class, and I don't have any students in front of me, I'm just going to sort of do one for you here. So it's already written down. I'll zoom in a little bit. Now would be the time that you should pause and maybe just copy this down and you can sort of see what we have going on here. So why don't you hit pause, copy this down. This was a jump that I did off a chair, and when you're done copying it, come on back and we'll start to talk through it. Okay, you've got this copied. So this is the trip of my big toe as I jump off of a chair. So let's start to talk about some of the pieces of information that we can find here from the graph or with respect to this whole situation. So what variable is being measured on the x-axis? Well, the x-axis is our independent, represents our independent variable. That's the one that kind of just does, and the other variable, the y or the vertical axis, is the one that responds to it. So in this case, as is often the case, maybe almost most of the time, we are going to be measuring time on our independent or x-axis, and we're going to be measuring that in seconds. The y-axis will be measuring the height of my toe as measured in, I believe it was meters, possibly. Yep, looks like meters. So as I said, often you have an independent variable on the x-axis being time. The y-axis variable, whatever it's representing, can actually be fairly varied. There's lots of things that it could be. So if we look at this parabola, this sort of imaginary parabola that follows the path of my toe, once I've jumped off of this, I think I call it a platform in the lesson, but it's like a chair or whatever. What is the direction of opening for this parabola? Well, we can see that if you can imagine this parabola kind of continuing, hits a high point, kind of comes back down, that's going to be opening down for sure. So opening down. Okay, so that's some of the preliminary stuff. Let's just get right into it now. So which point on the graph will tell us the height of the platform? So if we look at the graph, the height that I start from right here, it corresponds to, if you can imagine, at that moment in time, that's how high my toe is off the ground at the moment that I jump. So that time of 0, how high is my foot above or my toe above the ground? So at a time of 0, my foot's height is 0.75 meters. So 3/4 of a meter off the ground. And that corresponds to the y-intercept. And I want to make a note of that because anytime you're asked in a word problem to find a sort of an initial starting height of something or an initial starting value of something, that's going to be corresponding to the y-intercept. And we get the y-intercept from what form of the quadratic? That's standard form. So a question like this, you'd want to have your quadratic in standard form to get the information that you want. Now the information, as I said, was the height of the platform from which I jumped was 0.75 meters. That's the actual answer to the question. The rest of the stuff is just a little bit extra. We usually use, or I usually use this lesson as sort of a guide for how to solve word problems. And then we usually do a ton of them in class. It's a fairly short lesson. We're not going to get the benefit of that today, so I'll probably say it a couple more times. But if you get stuck on a word problem, I've done videos for lots of the word problems that are assigned as homework in this lesson. So please, please, please reach out if you get stuck, and I'll talk you through it for sure. Okay, so which point will tell us what my toe's maximum height was during its flight? That one might be obvious. That will be the vertex. So the vertex is the, let's change up our color palette here a little bit. So the vertex is going to be the highest point. The when does it happen is 0.5 seconds, and it reaches a maximum height of 0.8 meters. So the point that tells me this highest lowest point is, highest point, but what could also be the lowest point if we're talking about a vertex, or if we're talking about a highest or lowest point, will be the vertex. So that's the point that's telling us the optimal value, the highest or lowest that it reaches. So what's my toe's maximum height? It was 0.8 meters. And again, what form tells us the vertex? Obviously it's vertex form. Now you can get there from lots of different forms, but that's kind of the point, I think, is if you're given standard form and you need to find the vertex, well, we know how to transition from standard form to vertex form. We can either complete the square, or we can use the cheat, the h equals negative b over 2a, and then we can sub that value into the function and find f at h to get the k value of the vertex. So that's what we're after when we want the vertex. So how can we find out how long the toe was in the air? So this is a third and final point that we're going to be illustrating down here. Here we have the point at which, whoops, I want the highlighter there, the point at which we hit the ground. So if you look at from a time of 0 all the way to that point, that's how long it was in the air. So how long was it in the air? 2.5 seconds, and I know that that's the end of its trip because it's now at a height of 0. So we know that the toe was in the air for 2.5 seconds, and that's an x-intercept. And what form of a quadratic gives us the x-intercept? This is going to be from factored form. So a lot of times in word problems, when you're asked for when does something hit the ground, when did you break even, when does it, when does it cross that x-axis or hit a specific value, you're going to want to be using factored form for that. And we know how to get there, right? From standard form, you get to factored form by factoring. From vertex form, you can do a plot pattern, I guess, if you wanted to graph it, or you could expand it out to standard form and then factor it. So there's lots of different ways to get there. So that's actually the end of the lesson. We have the little sketch. Oh, actually, you know what? We got a little real life situation domain here. So let's talk about this. The domain, of course, are the independent variables values. You can see that it's continuous, so it's going to be the set of all x such that x is an element of real numbers. You'll see that the lowest point that we reach is 0, which is where we started. There's x. The highest point that we reach is 2.5. So we know that it's going to be less than or equal to 2.5. It hits 2.5, and 0 less than or equal to x, which is again just a fancy way of saying x will always have a value equal to or greater than 0, but also less than or equal to 2.5. So that is our domain. And I want to point this out for a real world situation because when we're dealing with just theoretical parabolas, and I said this often in the other lessons, the domain's wide open. There's no limits on it, just theoretically. However, if we're talking about the trip of my big toe, I can't go into negative values. I can't go backwards in time. I wish. And you can't go past 2.5 seconds because at that point my toe's kind of on the ground. I guess it could continue and we could just sort of have a different shape going at that point, but realistically, if we're just looking at the parabola, the journey starts at 0 and ends at 2.5, and those are the limits on our domain. Let's do a similar exercise with the range. So we can see the highest point that we reach is 0.8, and the lowest point is 0. So same thing, we have a nice continuous line, so the set of all y, such that y is an element of real numbers, where, so our low value is 0, our high value is 0.8, so we know that y will be less than or equal to 0.8, that's our high point, and that 0 will be less than or equal to y, which again is just another way of saying that our y value will be equal to or greater than 0, but also less than or equal to 0.8. And again, limits, it's not all of a sudden going to turn around and go higher than that. We're used to having a limit on the range, but this time there's also a low end limit, just meaning that my toe did not travel through the floor and into the ground. I guess if it did, we'd have a slightly different looking graph, but this is the graph that we've got. So as I said, we typically do lots of examples in class on the whiteboards that kind of get you into this zone, but let me just say one more time the three forms of the quadratic, so factored form, vertex form, and standard form, all three of them have one point that's easy to see. For standard form, it's the y-intercept. Those are often in word problems referred to as initial values. How high was the thing that you were starting on, something like that. The vertex from vertex form, clue words for that would be like, the highest point, the maximum point, the biggest, or even the smallest, the lowest point, something that deals with an extreme. And the last one is the x-intercept, brought to you by factored form, and those are often break-even points or points at which something hits the ground, and then you can see how long in the independent variable was the trip or the duration of time in the air or whatever. Again, it's hard to sort of talk about every single example you're going to see in the lessons, but there are a fair number of homework questions here to do. Make sure that you're not leaving any questions behind you're not sure of. As I said before, reach out if you get stuck. This is a challenging lesson to sort of transition from using just general forms of quadratics into those that are applicable in word problems. But the key to doing this homework is recognizing what point do I want and what form of the quadratic will give me that information, and then changing from whatever form of the quadratic you have into the one that you need. So that's the gist of it. Again, this is the last lesson in Unit 2B. It's a long, big unit is Unit 2, and 2B is long as well. So reach out with any questions you have in the homework. Reach out in person, by email, in our group chat that we have going every day. However you need to get a hold of me, we'll answer all your questions. And then after this, you're on to the assessment. So good luck on the assessment, and yeah, we'll see you in Unit number 3.